Welcome to our comprehensive sentence transformer tutorial. In this series, we'll be exploring one of the most powerful tools in modern natural language processing, sentence transformers. These models have revolutionized how we work with text by allowing us to convert sentences and paragraphs into meaningful numerical representations that capture their semantic meaning. We've structured this tutorial into 4 main chapters to guide you through your learning journey. In Chapter 1, we'll start with the fundamentals, getting you comfortable with the core methods and basic operations of sentence transformers. You'll learn how to install the library, load pre-trained models, and generate your first sentence embeddings. Chapter 2 takes us deeper into specialized encoding techniques and similarity computations. Here, we'll explore how to compare sentences, find similar texts, and use advanced encoding methods for specific use cases. In Chapter 3, we'll tackle the exciting topic of training and fine-tuning. You'll learn how to adapt these models to your specific domain or task, improving their performance for your particular needs. Finally, Chapter 4 focuses on the practical aspects of taking your models to production. We'll cover model management, optimization techniques, and best practices for deploying sentence transformers in real-world applications. Let's begin this exciting journey into the world of sentence transformers. Welcome to Chapter 1, Getting Started with Sentence Transformers, Core Methods. In this comprehensive tutorial, we're going to explore the fundamental building blocks of the sentence transformers library. We'll learn how to install and set up sentence transformers, understand the sentence transformer class initialization with all its parameters, master the core encode method and how it differs from forward, work with tokenization and model properties, understand embedding dimensions and sequence lengths, and visualize and analyze sentence embeddings. By the end of this tutorial, you'll have a solid foundation for working with sentence embeddings in your natural language processing projects. Let's start by setting up our environment. First, we need to install the required packages and import the necessary libraries. We'll also configure our environment for reproducible results, which is important for consistent experimentation. Now I'm going to install sentence transformers and set up our working environment. This core code will install all the necessary packages including sentence transformers, PyTorch, NumPy, Matplotlib, Seaborn, and scikit-learn. We'll import the sentence transformer class from sentence transformers, along with Torch and NumPy. I'll also set random seeds to 42 for both PyTorch and NumPy to ensure reproducible results. Finally, we'll check our PyTorch version and whether CUDA is available for GPU acceleration. Great, our environment is set up successfully. We can see we're running PyTorch version 2.80 plus CPU, and CUDA is not available, which means we'll be working on CPU for this tutorial. That's perfectly fine for learning these concepts, as the principles remain the same regardless of whether we're using CPU or GPU. Before we dive into the code, let's understand how sentence transformer processes text into embeddings. This image shows the complete pipeline from raw text input through tokenization, the transformer model, pooling, and optional normalization to produce the final sentence embeddings. Understanding this architecture helps us appreciate what happens under the hood when we call the encode method. The sentence transformer.init method is your entry point to loading and configuring sentence embedding models. Let's explore its parameters systematically to understand all the options available to us. Let me demonstrate the basic initialization of a sentence transformer model. We'll load a pre-trained model called AllMiniLM L6v2, which is a popular, lightweight model that provides a good balance between performance and speed. After loading, I'll verify that the model loaded successfully and has the essential encode method we'll be using throughout this tutorial. Perfect, the model loaded successfully. We can see the model architecture consists of 3 main components. First, a transformer layer that handles the BERT model with a maximum sequence length of 256 tokens. Second, a pooling layer that performs mean pooling across tokens to create a single embedding vector of 384 dimensions. And third, a normalized layer that ensures our embeddings have unit length, which is useful for similarity calculations. The model is running on CPU as expected. This table shows all the advanced initialization parameters available. The model name or path parameter determines which model to load. The device parameter lets you choose between CPU and GPU cache folder specifies where downloaded models are stored. Trust Remote Code allows loading custom models. Truncate dim can reduce the output embedding dimensions for efficiency. And the backend parameter lets you choose between Torch, UNCs, or OpenVINO for different optimization strategies. Now let's explore advanced initialization with custom parameters. I'll create a model with specific configurations including automatic device selection, a custom cache folder for storing models, and dimension truncation to reduce the embedding size from 384 to 256 dimensions. This truncation can be useful when you need to reduce memory usage or speed up similarity computations. Let me test this with a sample text to verify the truncation works correctly. Excellent, the truncation worked as expected. We successfully reduced the embedding dimension from the original 384 to 256 dimensions. The embedding has a norm of 0.8233, and we've verified there are no NaN values in the output. This dimension reduction technique can significantly reduce memory usage and computation time when working with large datasets. The encode method is the primary interface for converting text to embeddings. It's the high-level API that handles all preprocessing, model inference, and post-processing automatically. This image illustrates the key difference between encode and forward methods. Encode accepts raw text and returns NumPy arrays or tensors, while forward requires tokenized input and returns a dictionary. Let's explore encode in detail. Let me demonstrate basic encode usage with a single sentence. We'll encode the text, machine learning is fascinating, and examine the output structure. The encode method automatically handles tokenization, passes the tokens through the model, applies pooling, and returns a NumPy array by default. Perfect, we've successfully encoded our single text. The output is a one-dimensional NumPy array with 384 dimensions, matching our model's embedding dimension. The data type is float32, which is the standard precision for embeddings. We can see the first 5 values of our embedding vector, which are normalized floating point numbers representing the semantic meaning of our input text. Now let's encode multiple sentences at once using batch processing. This is much more efficient than encoding sentences individually. I'll encode 4 sentences about different AI topics, using a batch size of 2 and showing a progress bar to track the encoding process. This demonstrates how to efficiently process multiple texts in production scenarios. Excellent, we've successfully encoded all 4 sentences in 2 batches. The batch embeddings have the expected shape of 4 by 384, meaning 4 sentences each with 384 dimensional embeddings. The total memory usage is 6 kilobytes, which is quite efficient. Batch processing is significantly faster than encoding sentences one by one, especially when working with larger datasets. The encode method offers many parameters for fine-tuning the encoding process. Let's explore the most important ones with practical examples to understand when and how to use them. Let me demonstrate the normalize embeddings parameter, which is crucial for similarity computations. When we normalize embeddings, we create unit vectors where all embeddings have a length of exactly 1. This makes cosine similarity calculations more efficient and ensures that similarity scores are based purely on direction, not magnitude. I'll encode some animal and vehicle words both with and without normalization to show the difference. Interesting, in this case, the model already returns normalized embeddings by default, as we can see both unnormalized and normalized norms are essentially 1. This is because our model includes a normalization layer as its final step. However, it's still good practice to explicitly set normalize embeddings to true when you need unit vectors for similarity calculations, as not all models include built-in normalization. Now let's explore output format options. The encode method can return either NumPy arrays or PyTorch tensors, depending on your needs. If you're doing further processing with PyTorch, tensors are more convenient. For general-purpose use or integration with scikit-learn, NumPy arrays are typically preferred. Let me demonstrate both options. Perfect, we've successfully generated both output types. When we set convert to tensor to true, we get a PyTorch tensor that can be directly used in PyTorch operations. When we set convert to numpy to true, we get a numpy array. The tensor is on CPU as specified. This flexibility allows you to seamlessly integrate sentence transformers with your existing machine learning pipeline. Let me create a visualization to show how different encoding parameters affect the similarity between sentences. We'll compare 4 different configurations: default settings, normalized embeddings, truncated dimensions to 128, and both normalization and truncation combined. This will help us understand how these parameters impact the semantic relationships between sentences. This visualization clearly shows how different encoding parameters affect similarity scores. Notice that the default and normalized configurations produce nearly identical results because our model already normalizes by default. The truncated configurations, using only 128 dimensions instead of 384, still capture the main semantic relationships, but with slightly different similarity scores. Importantly, we can verify that I-related sentences, indices 0, 1, and 3, show higher similarity to each other than to the weather sentence at index 2, confirming that our embeddings capture semantic meaning correctly. The tokenize method gives you access to the intermediate tokenization step. This is useful for understanding how text is processed before being fed to the transformer model. Let's explore what happens during tokenization. Let me tokenize a simple sentence to see what the tokenizer produces. We'll examine the token structure and understand the different components returned by the tokenization process. The tokenizer converts our text into numerical representations that the model can process. The tokenization produced 3 key components. Input IDs are the numerical representations of our tokens, with special tokens 101 and 102 marking the beginning and end of the sequence. Token type IDs help the model distinguish between different segments in multi-sentence inputs. The attention mask tells the model which tokens to pay attention to, with 1 for real tokens and 0 for padding. Our sentence was tokenized into 9 tokens total, including the special tokens. Now let's compare tokenization for texts of different lengths to understand how the tokenizer handles varying input sizes. This is important for understanding the relationship between text length, token count, and the model's maximum sequence length limitation. We can see the relationship between text length and token count. The word short produces just 3 tokens, including special tokens. The medium length sentence with 41 characters produces 10 tokens, and the long sentence with 205 characters produces 39 tokens. This demonstrates that tokenization doesn't have a one-to-one correspondence with words or characters, as the tokenizer uses subword units that can represent parts of words or whole words depending on their frequency in the training data. Understanding model properties is crucial for working with embeddings effectively. Let's explore the key methods for inspecting model characteristics and understanding the constraints of our model. Let me query the model's key properties, specifically the embedding dimension and maximum sequence length. These properties are fundamental to understanding what our model can handle and what output to expect. I'll also verify that the reported dimensions match the actual output. Our model has an embedding dimension of 384, meaning every input text is converted to a 384-dimensional vector. The maximum sequence length is 256 tokens, which means any text longer than this will be truncated. We've verified that the actual output dimension matches the reported dimension. These constraints are important to keep in mind when designing your application. Let's test how the model handles text that exceeds the maximum sequence length. I'll create a very long text with 1,000 repetitions of the word, then tokenize it to observe the truncation behavior. This is important to understand because silent truncation can affect the quality of embeddings for long documents. As expected, the text was truncated to exactly 256 tokens, the model's maximum sequence length. Even though we provided 1,000 words, the tokenizer automatically truncated the input to fit within the model's constraints. This is important to remember when working with long documents, as you might lose information from the truncated portion. For long documents, consider splitting them into chunks or using models specifically designed for longer sequences. The forward method is the low-level interface that requires tokenized input, while encode is the high-level interface that handles everything automatically. Let's compare them directly to understand when you might use each one. Let me demonstrate the difference between forward and encode methods. We'll encode the same text using both methods and compare their outputs. The encode method handles text directly, while forward requires us to tokenize first and returns a dictionary with additional information. The outputs are identical with a cosine similarity of 1, confirming that encode internally uses forward. The key differences are that encode accepts raw text and returns a simple array, while forward requires tokenized input and returns a dictionary containing the sentence embedding. The encode method also handles batch dimension automatically, while forward preserves it. In practice, you'll almost always use encode, unless you need fine-grained control over the tokenization process or access to intermediate representations. Now let's apply what we've learned to build a simple semantic search system. This demonstrates the real power of sentence embeddings, the ability to find semantically similar content even when the exact words don't match. First, I'll create a document corpus covering various technology topics. We'll encode all these documents into embeddings, normalizing them for efficient similarity computation. This creates our searchable knowledge base, where each document is represented as a dense vector capturing its semantic meaning. Successfully encoded 10 documents into our embedding space. Each document is now represented as a 384-dimensional normalized vector. This vector representation allows us to compute semantic similarity between any query and our documents, enabling intelligent search that understands meaning rather than just matching keywords. Now I'll implement a semantic search function that takes a query, encodes it, and finds the most similar documents using cosine similarity. This demonstrates how embeddings enable us to find relevant content based on meaning rather than exact keyword matches. Let me test it with 3 different queries to show how it handles various search intents. Excellent results. For the query, "How do neural networks work?" the system correctly identified the deep neural networks document as most relevant, followed by machine learning. For programming languages for beginners, it found the Python document as the best match, which makes sense given Python's reputation for simplicity. And for security and protection, it correctly identified the cybersecurity document. This demonstrates that our semantic search understands the meaning and context of queries, not just keyword matching. Let me create visualizations to show the semantic structure of our document embeddings. We'll use PCA to reduce the embeddings to 2D for visualization and create a similarity heat map to show how documents relate to each other. This helps us understand the semantic space our model has created. These visualizations reveal the semantic structure captured by our embeddings. In the 2D PCA projection, we can see that related concepts cluster together. The similarity heat map shows strong connections between related topics. For example, ML and deep learning have high similarity of 0.74, while ML and cloud computing have lower similarity of 0.21. Python and data science also show good correlation at 0.41. This confirms that our embeddings successfully capture semantic relationships between concepts. Let's explore techniques to optimize encoding performance for production use cases. Understanding how batch size affects performance is crucial for scaling your applications. I'll test different batch sizes to understand their impact on encoding performance. We'll encode 100 test sentences with batch sizes ranging from 1 to 64 and measure the time taken. This will help us understand the optimal batch size for our hardware configuration. The results clearly show that larger batch sizes significantly improve throughput. With a batch size of 1, we process about 277 sentences per second. This improves to over 1,000 sentences per second with a batch size of 64. The performance gain is due to better utilization of vectorized operations. On GPU, these improvements would be even more dramatic. The key takeaway is to always use the largest batch size your memory allows for optimal performance. Let me visualize the performance characteristics with graphs showing encoding time versus batch size and the throughput achieved with different batch sizes. This will help us better understand the performance optimization opportunities. The visualizations clearly show the performance benefits of batch processing. The encoding time decreases as batch size increases, following a logarithmic curve that starts to flatten at larger batch sizes. The throughput bar chart shows we achieve nearly 4 times better performance with a batch size of 64 compared to processing sentences individually. On CPU, we're seeing good scaling up to batch size 64. On GPU, you'd typically see even better scaling, especially for larger batch sizes. Let's explore important considerations when working with sentence transformers in production environments. Understanding these pitfalls will help you avoid common mistakes. First, let's examine a common misconception about normalization and cosine similarity. Some developers worry about whether to normalize embeddings before computing cosine similarity. Let me demonstrate that cosine similarity inherently handles normalization, so the similarity scores are identical whether you normalize the embeddings or not. As demonstrated, the similarity matrices are identical with a maximum difference of essentially 0. This is because cosine similarity inherently normalizes vectors as part of its calculation. However, pre-normalizing embeddings can still be beneficial for storage efficiency and faster computation when you're doing many similarity calculations, as you can use simple dot products instead of full cosine similarity computation. Now let's understand memory requirements for embeddings. When working with large datasets, memory can become a constraint. I'll create a function to estimate memory usage and verify it with actual allocations. This helps you plan your infrastructure needs. Our memory estimation is accurate. For 100 sentences, we need just 0.15 megabytes, but this scales linearly. For 100,000 sentences, we'd need about 146 megabytes. For 1,000,000 sentences, that's 1.4 gigabytes. These calculations assume float 32 precision. You could have these requirements by using float 16, though with some potential loss in precision. Always consider memory requirements when designing systems that need to store many embeddings. Finally, let me demonstrate a best practice for encoding large datasets. Instead of trying to encode everything at once, which could cause memory issues, we'll process the data in chunks. This approach allows you to handle datasets of any size without running out of memory. We've successfully encoded 2,500 documents using chunked processing with 500 documents per chunk. The final embeddings have the expected shape and use about 3.66 megabytes of memory. This chunking approach is essential for production systems where you might need to process millions of documents. It also allows you to add progress tracking and error handling for each chunk, making your system more robust. Let's summarize what we've learned in this comprehensive tutorial. We've covered 6 core methods of the sentence transformer library. The init method for initializing models with various configurations. The encode method, which is the high-level API that handles everything from text to embeddings. The tokenize method for accessing intermediate tokenization. The getSentence embedding dimension method for querying output dimensions. The getMax sequence length method for understanding input limitations. And the forward method, which is the low-level API requiring tokenized input. We've also learned crucial best practices like always normalizing embeddings for similarity tasks, using appropriate batch sizes for your hardware, processing large datasets in chunks to manage memory, understanding the difference between encode and forward, monitoring sequence lengths to avoid truncation, and choosing the right backend for deployment. For performance optimization, remember that batch processing is significantly faster than individual encoding. GPU acceleration provides substantial speedups. Truncating dimensions can reduce memory and improve speed, and pre-computing and caching embeddings when possible saves computation time. You're now equipped to effectively use sentence transformers for semantic search, similarity computation, and other NLP tasks. That's all for this tutorial. Thank you for joining me in exploring the core methods of sentence transformers. I hope you found this comprehensive guide helpful for understanding how to work with sentence embeddings effectively. Happy coding! Welcome to Chapter 2, where we'll explore specialized encoding methods and similarity functions in sentence transformers. We're going to master how to encode queries differently from documents, understand various similarity metrics, and build practical retrieval systems. These techniques are fundamental for building real-world search and recommendation systems. Let's begin by setting up our environment and imports. We'll load the necessary libraries and initialize our sentence transformer model. Now we're importing our core libraries. We'll use NumPy for array operations, Torch for tensor computations, and sentence transformers for our encoding work. I'm using the All-Mini-LM L6v2 model, which is specifically optimized for retrieval tasks. This model provides a great balance between performance and speed. Perfect, our model is loaded successfully. We can see it has three main components: the transformer layer for processing text, a pooling layer that creates sentence embeddings from token embeddings using mean pooling, and a normalization layer. The model produces 384-dimensional embeddings and can handle sequences up to 256 tokens long. Let me also import some visualization and utility libraries that we'll use throughout this tutorial. Now we come to one of the key concepts in this chapter, the difference between query and document encoding. Sentence transformers provides three specialized encoding methods: encode query for search queries, encode document for documents or passages, and the general-purpose encode method. The key insight here is that queries and documents often have different characteristics. Queries tend to be shorter and more focused, while documents are longer and more comprehensive. Some models can leverage these differences for better retrieval performance. Let's see these different encoding methods in action. I'll create some sample queries and documents that represent typical search scenarios. Notice how queries are typically questions or short phrases, while documents are complete statements with more context. We'll encode both sets using the appropriate methods and verify that the shapes match our expectations. Excellent, all our encodings have the expected shapes. We have 3 query embeddings and 5 document embeddings, each with 384 dimensions. The general embeddings also have the same shape as our queries, which makes sense since we encoded the same query texts. Now let's examine how different encoding methods actually affect the embeddings. This is an interesting aspect because not all models have specialized prompts for queries versus documents. When a model doesn't have these prompts, all 3 methods produce identical results. Let's compare the query encoding with general encoding to see if there are any differences. We'll calculate both the maximum and mean differences between these encodings. This will tell us whether this particular model uses different processing for queries. As we can see, the query and general encodings are completely identical for this model. The maximum and mean differences are both 0. This tells us that the All-Mini-LM L6v2 model doesn't use specialized prompts for queries. However, models that do support prompts can show significant differences here, which can improve retrieval performance. Let's visualize the distribution of our embedding values to better understand their characteristics. Looking at these distributions, we can see that both query and document embeddings follow similar patterns. The embedding values are roughly normally distributed around 0, which is typical for well-trained models. The similar means and standard deviations across different encoding types confirm that this model treats them similarly. Now let's dive deeper into the encoding parameters. Both encode query and encode document support various parameters that give us fine control over the encoding process. This table shows all the available parameters, from batch size for processing efficiency to precision settings for memory optimization. Let me demonstrate these different output formats in practice. We can get our embeddings as NumPy arrays, which is the default PyTorch tensors for GPU operations, or normalized embeddings with unit length. Each format has its use cases depending on your downstream application. Perfect, we've successfully demonstrated all 3 output formats. The NumPy array is great for general-purpose use. Tensors are ideal when you need to do further GPU computations, and normalized embeddings ensure all vectors have unit length, which is crucial for certain similarity metrics. Precision is another important parameter that affects memory usage. Let's explore how different precision levels impact our embeddings. Lower precision can significantly reduce memory usage, which is valuable when working with large-scale systems. Interesting results here. Float32 is the default and uses 1536 bytes. But look at int8 and uint8, they only use 384 bytes, which is a 4x reduction in memory. This can be crucial when you're dealing with millions of embeddings in production systems. The model automatically handles quantization when you request lower precision. Now let's explore similarity functions, which are at the heart of retrieval systems. Sentence Transformer provides 4 built-in metrics. Cosine similarity measures the angle between vectors and is the most commonly used. Dot product is the raw dot product, which is very fast to compute. Euclidean and Manhattan distances are negated to convert them to similarity scores. Let's create some example text pairs to demonstrate similarity computation. I'm choosing pairs that have varying degrees of semantic similarity. The first pair is about Python programming, the second about machine learning, and the third about weather. We'll compute a full similarity matrix to see how each text in set A relates to each text in set B. Excellent, our similarity matrix shows exactly what we'd expect. The diagonal values are high, showing that semantically similar pairs have high scores. For example, the two Python-related texts have a similarity of 0.88, the machine learning text scores 0.64, and the weather text scores 0.67. The off-diagonal values are much lower, correctly identifying that unrelated texts have low similarity. Let's visualize this similarity matrix as a heat map to make the patterns more obvious. This heat map beautifully illustrates the similarity patterns. The red cells along the diagonal show high similarity between related text pairs, while the blue cells indicate low similarity between unrelated texts. This visual representation makes it easy to spot which documents would be retrieved for each query in a search system. Sometimes you don't need a full matrix, you just want to compare corresponding pairs. That's where similarity pairwise comes in. It computes similarity only between corresponding elements, returning a one-dimensional vector instead of a matrix. This is much more efficient when you have paired data. Let's compute pairwise similarities and verify they match the diagonal of our full matrix. This method is particularly useful when you're comparing versions of documents or evaluating paired translations. Perfect, the pairwise similarities match exactly with the diagonal of our similarity matrix. Each pair shows strong semantic similarity, with the Python pair scoring highest at 0.88. This confirms that pairwise similarity is essentially extracting the diagonal elements, but doing so more efficiently. Now let's explore how different similarity metrics behave. Each metric has different mathematical properties that make it suitable for different use cases. We'll test them on similar texts, different texts, and self-similarity to understand their characteristics. I'll test all 4 similarity functions with the same text pairs to see how they differ. We'll look at similar texts about NLP and transformers, completely different texts about the stock market, and self-similarity where we compare a text with itself. These results reveal important differences between metrics. Cosine and dot product give identical results here because our model normalizes embeddings by default. Both correctly identify similar texts with a score of 0.75 and different texts with negative scores. Euclidean and Manhattan distances are negative because they measure distance, so smaller values mean more similar. Notice how self-similarity is perfect one for cosine and dot, but 0 for distance metrics. Let's visualize these metric comparisons to better understand their discrimination power. This visualization shows 2 key insights. First, cosine and dot product behave identically when embeddings are normalized. Second, all metrics successfully discriminate between similar and different texts, as shown by the large difference in the right chart. The discrimination power is consistent across metrics, just with different scales. Normalization is a crucial concept that significantly affects similarity computations. Let's explore how normalization impacts different similarity metrics. This is especially important for understanding when cosine similarity and dot product are equivalent. We'll compare normalized versus unnormalized embeddings and see how they affect similarity scores. This will demonstrate a key mathematical relationship, that dot product of normalized vectors equals cosine similarity. This confirms an important mathematical fact. Cosine similarity is invariant to normalization. It always gives the same result whether vectors are normalized or not. However, dot product changes with normalization. When vectors are normalized to unit length, dot product becomes identical to cosine similarity. This is why many systems normalize embeddings by default. Now let's build a practical information retrieval system. This demonstrates how query and document encoding work together in a real application. We'll create a corpus of documents about various AI and programming topics, then search through them with different queries. I'll create a diverse corpus covering topics from Python programming to deep learning and cloud computing. Then we'll encode the corpus as documents and our searches as queries. Using cosine similarity, we'll find the top 3 most relevant documents for each query. Excellent retrieval results. For the transformers query, it correctly identifies the document about transformers with a high score of 0.69. For deep learning, it finds the deep learning document with 0.55 similarity. And for Python programming, it retrieves the Python document with 0.65 similarity. The system successfully matches queries to the most relevant documents in our corpus. Let's visualize these retrieval results to see the full similarity distribution for each query. These bar charts show the complete similarity landscape for each query. Red bars indicate high relevance above 0.5, blue bars show medium relevance above 0.3, and gray bars are low relevance. You can clearly see how each query has 1 or 2 highly relevant documents, with the rest falling off quickly. This is exactly the behavior we want in a retrieval system. When working with large datasets, batch processing becomes crucial for performance. Let's explore how different batch sizes affect encoding speed. This is essential knowledge for production systems. I'll generate a larger corpus and test different batch sizes to find the optimal configuration. We'll measure the time it takes to encode 100 documents with batch sizes ranging from 8 to 64. The results show a clear trend: larger batch sizes are more efficient. With a batch size of 64, we achieve the fastest encoding at just 0.12 seconds for 100 documents. This is almost twice as fast as a batch size of 8. The optimal batch size depends on your hardware, particularly GPU memory, if you're using CUDA acceleration. Let's visualize this performance data to see the relationship between batch size and encoding speed. This performance curve clearly shows the benefit of larger batch sizes. The encoding time decreases consistently as we increase the batch size, with diminishing returns at higher values. The optimal batch size of 64 provides the best performance for our setup. Let's summarize the key takeaways from this chapter. We've learned to use specialized encoding methods for queries versus documents, explored different similarity functions and their properties, understood the impact of normalization, and optimized performance with batch processing. These are fundamental skills for building semantic search and retrieval systems. Finally, let's put everything together in a complete retrieval pipeline. I'll create a simple retriever class that demonstrates best practices for indexing documents and searching through them. This class encapsulates everything we've learned about encoding, normalization, and similarity computation. Our simple retriever works perfectly. It successfully indexed 10 documents and found the most relevant ones for our query about neural networks. The top result with a score of 0.58 is indeed about neural networks, followed by related topics like deep learning and reinforcement learning. This demonstrates how all the concepts we've learned come together in a practical application. That concludes Chapter 2 on specialized encoding and similarity. We've covered a lot of ground, from understanding different encoding methods to building a complete retrieval system. Thank you for following along. Welcome to Chapter 3, Training and Fine-Tuning Sentence Transformers. In this chapter, we're diving deep into how to train and fine-tune sentence transformers for your specific use cases. We'll master the fit method for training, understand different loss functions and when to use them, configure training parameters and optimizers, implement evaluation strategies, and apply best practices for fine-tuning. These skills are essential for adapting pre-trained models to your domain-specific needs. Let's start by importing all the necessary libraries for training sentence transformers. We'll need NumPy for numerical operations, Torch for the underlying deep learning framework, and the Sentence Transformers library with its essential components like input example for data formatting, losses for different training objectives, and evaluation modules. I'm also setting random seeds here to ensure our results are reproducible, which is crucial for training experiments. Great, all libraries are imported successfully. We're ready to start building our training pipeline. Now I'm setting up some utility functions that will help us visualize our training progress. These helper functions will create plots for training loss curves and similarity score distributions, making it easier to understand how our model is learning. Before we dive into the code, let's understand the overall training architecture for sentence transformers. This diagram shows how the different components work together. We have our input data flowing through the model, which consists of a transformer encoder followed by a pooling layer. The embeddings are then used to compute a loss based on our training objective, whether that's cosine similarity, triplet loss, or another approach. The gradients flow back through the network to update the model weights. Understanding this flow is crucial for effective training. Let's begin with Part 1, Basic Training Setup. We'll start with the simplest possible training example by creating synthetic data with learnable patterns for different classes. This helps us understand the fundamentals before moving to real-world data. Here I'm creating a function to generate synthetic training data with class-specific patterns. This is a powerful technique for understanding how the model learns. We're creating two types of patterns, tech terms like algorithm, neural, and model, and science terms like quantum, molecule, and gravity. For similar pairs, we use terms from the same domain and assign high similarity scores around 0.8 to 1. For dissimilar pairs, we mix terms from different domains and assign low scores around 0 to 0.2. This creates a clear learning signal for the model to distinguish between similar and dissimilar text pairs. Perfect, we've created 200 training examples. You can see an example of a similar pair about algorithms with a high similarity label of 0.875. This synthetic data will help our model learn to distinguish between semantically similar and dissimilar text pairs. Now let's initialize our model. I'm using All-Mini-LM L6v2, which is a small but effective model that's perfect for demonstrations and fast training. It has a maximum sequence length of 256 tokens and produces 384 dimensional embeddings. Let me verify that the model is properly loaded and can encode text. Excellent. The model is loaded successfully with a maximum sequence length of 256 tokens and produces embeddings of dimension 384. This compact embedding size makes it efficient for similarity computations while still capturing rich semantic information. Now we move to Part 2, Understanding Loss Functions. Different loss functions are designed for different data formats and training objectives. This diagram illustrates the key loss functions available in sentence transformers. Each loss function has specific requirements for input data format and is optimized for different tasks. Choosing the right loss function is crucial for training success. Let's start with cosine similarity loss, which is the most straightforward loss function for paired data with similarity scores ranging from 0 to 1. This loss function directly optimizes the cosine similarity between sentence embeddings to match the provided labels. I'm creating a data loader to batch our training examples and initializing the cosine similarity loss. The data loader handles shuffling and batching, which are essential for effective training. With a batch size of 16, we'll have 13 batches to process our 200 examples. The setup is complete. We have 13 batches with a batch size of 16, and our loss function is ready. The cosine similarity loss will directly optimize the cosine similarity between our sentence pairs. Now let's explore multiple negatives ranking loss, or MNRL. This is a powerful contrastive learning approach that uses in-batch negatives. For each query in a batch, all other positive examples in the same batch serve as negatives, making it highly efficient for retrieval tasks. For MNRL, we only need query and positive pairs, no explicit negatives. The loss function automatically treats other positives in the batch as negatives for each query. I'm creating examples with queries about machine learning concepts and their corresponding positive matches. With a batch size of 8, each query will have 7 in-batch negatives to learn from. We've set up 30 MNRL examples with a batch size of 8. This means each query will contrast against 7 in-batch negatives during training, providing a rich learning signal for retrieval tasks. Part 3 covers the fit method, which is the core training interface. This method has many parameters that control every aspect of training, from optimization to evaluation. Let me demonstrate all the key parameters with a comprehensive example. I'm setting up a complete training configuration with evaluation. First, I create an evaluator with sentence pairs and similarity scores to monitor training progress. Then I define all training parameters explicitly. We're using AtomW Optimizer with a learning rate of 2e-5, warm-up linear scheduler with 10 warm-up steps, weight decay of 0.01 for regularization, and evaluation every 50 steps. The model will save checkpoints and will limit gradient norms to 1 for stability. Training parameters are configured. We're using a learning rate of 2e-5, 10 warm-up steps, and weight decay of 0.01. These are good starting values for fine-tuning pre-trained models. Let's visualize how different parameters affect training behavior, particularly focusing on learning rate schedules. I'm creating a visualization to compare different learning rate schedules. The warm-up linear schedule gradually increases the learning rate during warm-up, then linearly decreases it. The warm-up cosine schedule follows a similar warm-up, but uses a cosine annealing for the decay phase. The right panel zooms in on the warm-up phase to show how the learning rate ramps up from 0, which helps stabilize early training. The visualization clearly shows the difference between warm-up linear and warm-up cosine schedules. Notice how both start with a gradual warm-up phase to prevent instability, then decay differently. Warm-up linear provides a steady decrease, while warm-up cosine offers a smoother transition that can sometimes lead to better final performance. Part 4 explores the complete training loop and evaluation process. This diagram illustrates how data flows through the training pipeline, from batching through forward pass, loss computation, backpropagation, and parameter updates. Understanding this flow helps you debug training issues and optimize performance. Now let's implement training with progress tracking using callbacks. I'm implementing a custom callback to track training progress. This callback will be called after each evaluation, recording the score, epoch, and step count. We'll train the model for 3 epochs with evaluation every 25 steps. The callback gives us detailed insight into how the model improves during training. Excellent! Training completed with 4 evaluations. You can see the callback being triggered at different points, showing perfect evaluation scores of 1 after the initial training. The model achieved strong performance with a final training loss of about 0.018. Let me visualize the training progress by plotting the evaluation scores over time. This helps us understand how quickly the model learns and whether it's converging properly. The training progress plot shows rapid improvement in the evaluation scores. The model quickly reaches high performance, demonstrating effective learning from our synthetic data. The annotations show the exact scores at each evaluation point. Part 5 covers multitask learning. Training with multiple objectives simultaneously allows the model to learn from different types of supervision signals, often resulting in more robust representations. I'm setting up multitask learning with 2 different objectives. First, we have similarity pairs with cosine similarity loss for learning direct similarity relationships. Second, we have triplets with triplet loss for learning relative distances, where each triplet contains an anchor, a positive example that should be close, and a negative example that should be far. The model will alternate between these objectives during training, learning complementary aspects of semantic similarity. multitask setup is complete with two objectives. The cosine similarity loss has 7 batches, and the triplet loss also has 7 batches. During training, the model will learn from both types of supervision, creating more robust embeddings. Part 6 explores different evaluators that measure various aspects of model performance. Each evaluator is designed for specific tasks and metrics. I'm creating 3 different types of evaluators. The triplet evaluator checks if the model correctly ranks positive examples closer than negative ones. The binary classification evaluator treats similarity as a classification task, measuring metrics like F1 score. The sequential evaluator combines multiple evaluators to get comprehensive performance metrics. Let me run a quick evaluation to show the output format. The evaluation returns a Pearson correlation of about 0.73 and Spearman correlation of 0.5. These metrics measure how well the model's similarity scores correlate with the ground truth labels. Let me visualize a comparison of different evaluation metrics to show what aspects of performance each one measures. This comparison shows different evaluation metrics and their typical scores. Cosine similarity measures direct similarity correlation. Triplet accuracy shows how often the model correctly ranks triplets. Binary F1 measures classification performance. MAP at 10 and NDCG are retrieval metrics. Each metric provides different insights into model performance. Part 7 demonstrates a complete fine-tuning pipeline for a domain-specific task. We'll simulate adapting a model to medical domain text with realistic synthetic data. I'm creating domain-specific medical data with realistic patterns. The data includes medical terminology like symptoms, conditions, and treatments. For similar pairs, we connect related medical concepts with high similarity scores. For dissimilar pairs, we use unrelated medical terms with low scores. This simulates the kind of domain adaptation you do with real medical text data. Domain-specific dataset created successfully with 300 training samples and 50 evaluation samples. This gives us enough data to demonstrate meaningful fine-tuning while keeping training time reasonable. Now let's fine-tune the model on our medical domain data. I'll first evaluate the initial performance to establish a baseline, then train with optimized parameters, including a higher learning rate of 5e-5, which is typical for fine-tuning. We'll track the improvement to see how much the model adapts to the domain-specific patterns. Impressive results. The model improved from an initial Pearson correlation of 0.575 to 0.949. That's a 65% improvement. This demonstrates how effective fine-tuning can be for domain adaptation. The model has successfully learned the patterns in our medical domain data. Let me visualize the embedding space to show how the fine-tuned model organizes the medical text. I'll use PCA to reduce the embeddings to 2D and color code them by similarity scores. The embedding space visualization shows how the model has learned to organize medical texts. Points with similar colors, representing similar texts, cluster together in the embedding space. The first principal component explains most of the variance, showing that the model has learned a strong primary dimension for similarity in this domain. Part 8 covers advanced training techniques. Let's start with gradient accumulation, which allows us to simulate larger batch sizes when memory is limited. I'm demonstrating gradient accumulation by using a small physical batch size of 8, but simulating an effective batch size of 32. This technique is crucial when you want the benefits of large batch training, but are limited by GPU memory. The model will accumulate gradients over 4 small batches before updating weights, effectively training with a batch size of 32. We're simulating gradient accumulation with a physical batch size of 8 and an effective batch size of 32. This gives us 152 steps per epoch. This technique allows you to train with larger effective batch sizes even on limited hardware. Now let's discuss automatic mixed precision, or AMP, which can significantly speed up training on compatible GPUs by using lower precision calculations where possible. I'm checking if AMP is available in the current environment. AMP uses mixed precision, combining float 16 and float 32 operations to speed up training while maintaining numerical stability. It requires a CUDA-capable GPU to be effective. AMP is not available in the CPU environment, but when enabled on a GPU, it provides approximately 2x faster training, reduced memory usage, and maintains training stability with proper gradient scaling. It's a must-use feature for GPU training. Let's explore checkpoint management for saving and resuming training. I'm setting up checkpoint configuration to demonstrate how to save training progress. Checkpoints allow you to resume training if interrupted, keep the best performing models, and track training history. We're configuring it to save every 50 steps and keep only the 3 most recent checkpoints to manage disk space. Checkpoint configuration is set up to save every 50 steps and keep the 3 most recent checkpoints. This ensures you can always resume training and won't lose progress if training is interrupted. The checkpoint directory has been cleaned up after the demonstration. Part 9 covers key strategies for optimal training performance. Understanding these trade-offs is crucial for efficient training. Let me visualize the trade-offs between different batch sizes. Larger batch sizes use more memory and provide better gradient estimates, leading to more stable training and often better final performance. However, they also have diminishing returns, as you can see the model quality plateaus around batch size 64 to 128. The visualizations show 3 key trade-offs. Memory usage grows linearly with batch size. Training throughput increases sublinearly due to better GPU utilization. Model quality improves with larger batches but plateaus, showing diminishing returns. The sweet spot is often between 32 and 64 for most tasks. Let's summarize the key takeaways and best practices from this chapter. For loss function selection, use cosine similarity loss for regression with similarity scores, multiple negatives ranking loss for retrieval tasks, and triplet loss for learning relative distances. For training parameters, start with a learning rate of 2e-5, increase to 5e-5 for fine-tuning, use warm-up for about 10% of total steps, and balance batch size between memory constraints and convergence quality. For evaluation strategy, evaluate frequently during training. Every 10 to 20% of an epoch, use task-specific evaluators, and combine multiple evaluators for comprehensive assessment. For performance optimization, enable AMP on compatible GPUs, use gradient accumulation for effective large batches, and implement checkpointing for long training runs. For domain adaptation, always start from pre-trained models, use domain-specific data with clear patterns, and fine-tune with higher learning rates initially. These practices will help you successfully train and fine-tune sentence transformers for your specific needs. That's all for Chapter 3 on training and fine-tuning sentence transformers. Thank you for joining me in this comprehensive exploration of training techniques. You now have the knowledge to effectively train and adapt sentence transformers for your specific use cases. Happy training! Welcome to Chapter 4, Production and Model Management. In this chapter, we'll explore how to effectively save, load, and deploy sentence transformer models for production use. We'll cover everything from model serialization using the Saphatensors format to deploying models on Hugging Face Hub, optimizing performance with multiprocessing across GPS and CPS, and implementing best practices for production deployments. Let's start by understanding the complete workflow from development to production deployment. This diagram shows the production model management architecture, illustrating how models flow from training through optimization and deployment to production systems. First, let's import all the required libraries we'll need for this chapter. We're bringing in sentence transformers for our embedding models, Torch for deep learning operations, NumPy for numerical computations, and various utilities for file handling, timing, and visualization. We'll also set up our visualization style using Seaborn and Matplotlib to create clear, professional-looking plots. Let me check what device we're working with, whether we have GPU support available. Great, we can see that we're using CPU for this tutorial with no GPS available. That's perfectly fine for learning these production deployment concepts. All the techniques will cover work equally well on both CPU and GPU environments. Now let's dive into model saving and serialization. The sentence transformer save method is the primary way to persist your trained models to disk. This method takes several important parameters. The path parameter specifies where to save the model_name allows you to give it a custom name. Create_model_card generates a README with model information which is crucial for documentation. Train_datasets records what data was used for training. And safe_serialization, which defaults to true, uses the safatensors format that's more secure and efficient than traditional pickle files. Let me demonstrate the save method in action. I'll load a pre-trained model, all-mini-LM L6v2, which is a lightweight but effective embedding model. Then, I'll create a temporary directory for our demonstration and save the model with all the important parameters. Notice how we're using safe_serialization equals true to use the safatensors format, which is the recommended approach for production. We're also specifying training datasets and creating a model card for documentation. Perfect! The model has been saved successfully. You can see all the files that were created, including the pooling configuration, normalization settings, the README model card, various configuration files, the actual model weights in safatensors format, and the tokenizer files. We've also verified that the model can be loaded back correctly and has the same embedding dimension, confirming our save and load process works perfectly. The save_pretrained method is another way to save models that follows Hugging Face naming conventions. This method is functionally identical to the save method, but ensures compatibility with the broader Hugging Face ecosystem, which is important when you're planning to share your models or integrate with other Hugging Face tools. Let me demonstrate save_pretrained and compare it with the regular save method. I'll save the same model using save_pretrained to a different directory, and then compare the file structures produced by both methods. Excellent! As you can see, both save and save_pretrained produce the same file structure with 12 common files. This confirms that both methods are compatible, and you can use either based on your preference or ecosystem requirements. Now let's explore how to deploy models directly to the Hugging Face Hub. The push_to_hub method enables you to share your models with the community or deploy them for production use. Key parameters include repo_id for your repository name, token for authentication, commit_message for version tracking, and various options for privacy and tagging. Here's a demonstration of the hub push configuration. In a real production scenario, you would provide your actual Hugging Face token and repository name. Notice how we're specifying training datasets, tags for discoverability, and whether the repository should be private or public. The safe_serialization parameter ensures we're using the secure format even when pushing to the hub. This shows the complete configuration for pushing a model to Hugging Face Hub. In production, this would actually upload your model and return a URL where it can be accessed. The tags help others discover your model, and the training datasets provide important provenance information. For production workloads, multi-process encoding is crucial for achieving high throughput. This diagram illustrates how multi-process architecture distributes encoding tasks across multiple GPS or CPU cores. The system uses input and output queues to manage work distribution, with each worker process loading its own copy of the model for parallel processing. Let me demonstrate multi-process encoding concepts. First, I'll show how the system determines available devices and sets up the multi-process pool. In production, you would use start_multi_process_pool to create worker processes, encode_multi_process to distribute the encoding work, and stop_multi_process_pool to clean up resources. Let's also benchmark single-process encoding to establish a baseline for comparison. We can see that single-process encoding achieved about 673 sentences per second on our test data. The multi-process architecture includes input queues for distributing batches, worker processes that each load the model independently, output queues for collecting results, and a process pool for managing the worker lifecycle. With 10 CPU cores available, we could expect around 3.5 times speedup with multiprocessing, potentially reducing our encoding time from 149 milliseconds to about 42 milliseconds for this batch. Matryoshka embeddings are a powerful feature that allows you to truncate embeddings to different dimensions while maintaining performance. This is incredibly useful for production scenarios where you might need different embedding sizes for different use cases, such as using smaller embeddings for initial retrieval and larger ones for re-ranking. Let me demonstrate the truncate_sentence_embeddings method. This uses a context manager pattern, which means the truncation only applies within the with block and automatically reverts to the original dimension afterwards. I'll show truncation to different dimensions like 64, 128, and 256 from our original 384-dimensional embeddings. Perfect! You can see how we successfully truncated embeddings to 64, 128, and 256 dimensions within the context manager. Each truncation produced embeddings of exactly the specified dimension. Most importantly, once we exit the context manager, the model automatically returns to its original 384-dimensional output. This makes it very safe and convenient to use different dimensions for different parts of your application. Now let's visualize the performance characteristics of different configurations to guide our production deployment decisions. Understanding how batch size affects encoding time, throughput, and memory usage is crucial for optimizing your production system. I'll create a benchmarking function to test different batch sizes and measure their performance characteristics. We'll test batch sizes from 1 to 64 and track encoding time, throughput, and estimated memory usage for each configuration. The visualization shows 3 key metrics. First, encoding time increases with batch size but not linearly, showing the efficiency gains of batching. Second, throughput improves significantly with larger batches, demonstrating the importance of batch processing for production systems. Third, memory usage grows linearly with batch size, which is an important constraint to consider. The performance summary shows that larger batch sizes generally achieve better throughput, with batch 64 achieving the highest sentences per second rate. Implementing proper version management is crucial for production deployments. Let me show you a practical approach to versioning and managing multiple model versions. This is essential for A/B testing, gradual rollouts, and maintaining backward compatibility. I'll create a model version manager class that handles saving, loading, and tracking multiple model versions with metadata. This system stores each version in its own directory, maintains a central version's JSON file with metadata, and provides methods to save new versions, load specific versions, and list all available versions. Let me demonstrate by saving 3 different versions representing development, staging, and production stages. Excellent, we've successfully created a version management system. We saved 3 versions with different stages and accuracy metrics. The system tracks each version's path, timestamp, embedding dimension, and custom metadata. We can list all available versions and see their stages and accuracy scores. Finally, we successfully loaded the production version 2.0.0, confirming our version management system works correctly. Now let's look at a comprehensive production deployment class that incorporates all the concepts we've covered. This production embedder class includes optimization features, monitoring capabilities, and production-ready error handling. I'm creating a production embedder class that wraps our sentence transformer with production features. It includes metrics tracking for monitoring performance, support for dynamic truncation, error handling, and clean resource management. Let me test it with different configurations, including various batch sizes and truncation dimensions, to ensure it handles all production scenarios correctly. Perfect! Our production embedder successfully handled different configurations. With batch size 16 and no truncation, we got 384-dimensional embeddings. With batch size 32 and truncation to 256, we got the expected reduced dimensions. And with batch size 64 truncated to 128 dimensions, everything worked as expected. The production metrics show we processed 3 requests totaling 112 sentences, with an average latency of about 40 milliseconds and 0 errors. This demonstrates a robust production-ready implementation. Real-time monitoring is crucial for production deployments. Let me create a simulation of monitoring, embedding performance over time to show what a production monitoring dashboard might look like. I'll simulate production load and create a monitoring dashboard with 4 key visualizations. We'll track request latency over time, encoding throughput, request queue size, and latency distribution with percentiles. The monitoring dashboard shows 4 critical metrics for production systems. The latency graph shows how response times vary over time, helping identify performance degradation. The throughput chart displays sentences processed per second, indicating system capacity. The queue size visualization helps detect bottlenecks, with a warning threshold at 15 requests. The latency distribution histogram shows P50 and P95 percentiles, which are crucial SLA metrics. Our simulation processed 15 requests with mean latency around 21 milliseconds and P95 latency at about 39 milliseconds, achieving roughly 635 sentences per second throughput. Production systems need robust error handling and recovery mechanisms. Let me show you how to implement a resilient embedder with retry logic, circuit breaker pattern, and fallback mechanisms. I'm creating a resilient embedder class that implements several production resilience patterns. It includes automatic retry with exponential backoff, a circuit breaker that opens after repeated failures to prevent cascade failures, fallback to a secondary model when the primary fails, and degraded responses as a last resort. The circuit breaker pattern is particularly important as it prevents the system from repeatedly trying a failing service, giving it time to recover. Great! Our resilient embedder successfully encoded 5 sentences in normal operation, producing embeddings of shape 5 by 384. In a real production scenario, if the primary model fails repeatedly, the circuit breaker would open and the system would automatically switch to the fallback model, ensuring service continuity even during failures. Let's summarize the key recommendations for production deployment. These best practices cover serialization, documentation, multiprocessing, versioning, monitoring, error handling, truncation, and hub integration. Each practice is paired with specific implementation details to guide your production deployments. Finally, let me create a production readiness checklist function that verifies a model is ready for deployment. This automated checklist tests model loading, encoding functionality, dimension consistency, serialization, performance, and memory usage. Excellent, all checks passed. The model loads correctly, encoding works properly, dimensions are consistent, serialization is functional, performance is acceptable with sub-5-second processing for 100 sentences, and memory usage is reasonable. The model is production-ready and good to deploy. We've now covered all the essential aspects of deploying sentence transformers to production. We learned about model serialization using save and save underscore, pre-trained with SAFA-Tensor's format, hub integration for deploying models with push underscore to underscore hub, multiprocess encoding for scaling across multiple GPS and CPS, Matryoshka embeddings for flexible dimension truncation, systematic version management, production patterns, including circuit breakers and monitoring, and performance optimization through batch processing. These techniques ensure your sentence transformer models are robust, scalable, and maintainable in production environments. That's all for Chapter 4 on production and model management. Thank you for following along. You now have a comprehensive understanding of how to deploy sentence transformers to production, from basic serialization to advanced monitoring and error recovery. These skills will help you build robust, scalable embedding systems for real-world applications.